First fact, time and space flows differently, and this is not a metaphor, but a tedious engineering necessity. Without Einstein's corrections, navigation satellites would turn into useless balls with solar panels. In orbit, two effects immediately collide. According to the special theory of relativity, fast-moving clocks tick slower. The satellite rushes at several kilometers per second and slightly lags behind. According to the general theory of relativity, weaker gravity unleashes time. At altitude, it flows faster than below in Earth's gravity well. These two flows, which diverge from everyday logic, add up to a strange outcome. Orbital atomic clocks gain tens of microseconds per day, estimated at about 38 microseconds. It seems like a tiny amount, but it's enough for the positioning error to grow every hour and accumulate kilometers in a day. Therefore, even on Earth, a frequency correction is embedded in the satellite's body, and the software constantly accounts for speed, altitude, the deformation of the Earth's geoid, and even the influence of tides. In 1971, the Hofela-Keating experiment with flights in atomic clocks confirmed that moving clocks along different trajectories changes the accumulated time. Today, this paradox lives in your smartphone. The map plots the route because orbital clusters and ground stations continuously synchronize the now for different points in space. On the International Space Station, clocks also travel differently. A cosmonaut returning after a long shift becomes fractions of a second younger than their earthly peers. Space literally stretches and compresses time, and humanity has learned to account for it in frequency tables and lines of code. Second fact, most of the universe is invisible and elusive. Familiar matter, stars, planets, gas clouds, bodies, and instruments constitutes only a small fraction of the cosmic balance, estimated currently at around 5%. The rest is divided between two shadows, dark matter and dark energy. The former is revealed by gravitational effects. Galaxies rotate faster than visible mass alone would allow, and without an invisible scaffolding, their disks would disperse. Galaxy clusters distort the light from distant sources, creating arcs and curved mirrors in telescope images. This is gravitational lensing, acting like a cosmic X-ray for invisible matter. The well-known bullet cluster shows that dark matter passes through opposing clouds almost without collision, leaving hot gas behind and the center of mass ahead. Dark energy is even more mysterious. According to observations of Type A supernovae and the cosmic microwave background, the universe's expansion is not just continuing but accelerating, as if space were permeated by a uniform anti-gravitational pressure. The numbers fluctuate from analysis to analysis, but the order is roughly this. About a quarter of cosmic content is dark matter, and about two-thirds is dark energy. Neither has yet been detected in a test tube. Search detectors in underground labs register only the rarest hints. Nevertheless, it is these invisible components that shape the cosmic foam of filaments and voids on scales of hundreds of millions of light-years and determine the fate of everything, from the shape of galaxies to the distant future in which the acceleration will likely continue. Third fact. The oldest photograph of the universe is not an image in visible light, but a uniform, almost identical whisper of microwaves from all directions with a temperature of about 2.7 Kelvin, the cosmic microwave background radiation. It was born when the young cosmos cooled to the point where electrons and protons could bind to form neutral hydrogen. This happened about 380,000 years after the Big Bang. Before that, the plasma was opaque and light was constantly scattered. Then the universe became transparent, and photons freely rushed through space, many of them reaching our detectors today. The discovery story is almost mundane. In 1965, Arno Penzias and Robert Wilson were hunting for mysterious radio noise, calibrating equipment, cleaning the antenna of pigeon droppings, and the noise wouldn't disappear because it was the entire universe speaking into our ear. Later, the COBE, WMAP, and Planck satellites unfolded this background into a map of the slightest inhomogeneities, fluctuations of a 10,000th of a degree, like crumpled folds on a smooth blanket. In these wrinkles lies the acoustics of the early plasma, the harmonics of oscillations, from which the curvature of space, almost flat, the proportions of matter, ordinary matter, dark energy, and an age of about 13.8 billion years were reconstructed. The polarization of the background indicates when the first stars reionize the gas, and gravitational lensing crumples the pattern, revealing the distribution of mass along the path. Scientists continue the hunt for primordial B modes, the imprint of gravitational waves from the inflation era. There is no conclusive evidence yet, but the mere possibility of hearing the echo of the first moments makes this matte microwave noise one of the most informative things ever measured by humans. Fact 4. Neutron stars are the remnants of exploded massive stars, whose core collapsed into a sphere about 20 kilometers in diameter, but with a mass of about 1.5 suns. The density there is close to nuclear density. A teaspoon of such matter would weigh about 1 billion tons on Earth. On the surface, gravity is hundreds of billions of times stronger than Earth's. One step would turn into an instant impact with the crust, and mountains barely grow higher than a few millimeters. The magnetic fields of some neutron stars, magnetars, are estimated to reach 10 to the 10 to 10 to the 11 Tesla, so much so that chemical bonds and electron orbits behave differently under such conditions, and star quakes in the crust generate gamma-ray bursts noticeable across half the galaxy. Their rotation is another record. There are millisecond pulsars making hundreds of revolutions per second. The absolute champion today spins faster than 700 times per second, and each flash is a lighthouse, a beam of radio waves cutting through space with each rotation. Pulsars were discovered in 1967 by graduate student Jocelyn Bell Burnell. At first, the signal seemed too regular, and jokingly received the label "signal from aliens." But it soon became clear it was a new stage of stellar life. The paradox of these objects is that they are simultaneously simple and predictable, like gyroscopes, and wild. Their periods suddenly stumble in glitches, magnetic storms break the crust, and interaction in binary systems speeds up and colors the beams. In telescopes, they are points, but by physics standards, a neutron star is a laboratory of extreme regimes, where theories of matter, magnetism, and gravity are tested. Fifth fact: black holes are not absolutely black. According to modern quantum field theory, on a curved background, they emit like cold furnaces. This is Hawking radiation. It can be imagined like this. The vacuum near the event horizon seethes with short-lived particle pairs, fluctuations. In the curvature of space, one particle can fall beyond the horizon while the second escapes outward as a real quantum. The energy for this is cut out from the hole's mass. The formula gives a temperature inversely proportional to mass. For solar mass, it's a tiny few tens of nanokelvins. And for supermassive monsters at the centers of galaxies, negligible fractions of a trillionth of a degree. They are colder than the cosmic microwave background and, essentially, absorb more than they emit. But something else is fundamentally important. A black hole has entropy, proportional to the area of the horizon, Bekenstein-Hawking law, and an analog of the second law. In the classical sense, the area does not decrease, just like entropy in thermodynamics. This subverts intuition. An object that releases nothing turns out to be thermodynamically warm, and its evaporation is a real process, just monstrously long, for stellar mass numbers with tens of zeros of years. From this arises the information paradox. If everything falling inside is ground into a faceless thermal spectrum, where does the information about the details go? Ideas of the holographic principle, quantum entanglement at the horizon, firewalls, and soft hair are attempts to reconcile gravity with quantum mechanics. We have already photographed the shadow of a supermassive hole against bright gas, and hear much lighter ones merging. But Hawking radiation is too weak to catch with a telescope. The fact remains stunning. The boundary from which nothing returns still whispers to the world, cold, quiet, and inevitable.
Sixth fact, the universe can sound, not in the air, but in the fabric of space. Gravitational waves are barely perceptible ripples that stretch and compress distances. They were first directly caught on Earth by giant rulers of L-shaped interferometers, two vacuum arms of several kilometers in which a laser beam runs 1,000 times between mirrors. When a wave passes, the lengths of the arms change by fractions of a proton's diameter, and interference produces a flash of signal, a chirp. Frequency and amplitude grow until two massive sources, black holes or neutron stars, merge into one. The first singing came from a pair of stellar mass black holes. Several solar masses of energy went into space ripples in hundredths of a second. The merger of neutron stars, on the other hand, showed a true cosmic symphony. Gamma rays, an optical kilonova, and the radio echo of a shockwave flashed simultaneously, making astronomy truly multi-messenger for the first time. It is in such explosions, according to models and spectra, that a significant portion of the heaviest elements, gold, platinum, lanthanides, are born. Their atomic nuclei are sculpted by rapid neutron capture in the densest environment. A network of detectors on different continents catches the same waves with a millisecond difference, allowing triangulation to point to a piece of sky where telescopes are already searching for light. Another front is the pulsar clocks across the galaxy. Regular radio beacons hint at the hum of ultra-long waves from giant black holes in the centers of distant galaxies. Gravitational waves have turned the cosmos from a silent movie into a sound one. Now we not only see, but also listen to how darkness is made. The discovery of exoplanets has transformed the cosmos from an abstract darkness into an inhabited map, although these worlds are almost always invisible. We learn about them through tiny dips in light. When a planet passes across a star's disk, its brightness drops by a fraction of a percent, as if someone placed a coin on a spotlight. This step in the brightness curve reveals the radius and orbit, and even hints of cloudiness and tilt from the fine details of entry and exit. Another method is the star's wobble. It's pulled by an unseen neighbor, and the star's spectral lines shift back and forth at speeds of meters per second. There are rarer tricks, gravitational microlensing, where the mass of a randomly passing star briefly magnifies distant light and reveals a planet as a fellow traveler, and direct imaging with coronagraphs, which literally block out the star's dazzling disk to catch a faint dot nearby. The catalogs from the Kepler and TESS missions, and now the shark ears of James Webb, have revealed the main thing. Planets are not the exception, but the rule. Statistically, most stars have planetary families. Among them are hot Jupiters, orbiting a star in a few days, super-Earths, which have no analog in our system, and compact ensembles like TRAPPIST-1, where 7 worlds are crammed into a dense string, and several receive as much heat as Earth. Transit spectroscopy allows us to sniff their atmospheres. Bands of water vapor, sodium, carbon dioxide emerge against the backdrop of starlight. Phase curves draw thermal maps where the day side sizzles and the night side cools under stellar wind. The habitable zone is just a balance of heat. Life is not written by geography. Worlds near red dwarfs can be tidally locked on one side to the star and suffer flares, and atmospheres can evaporate. But even with these caveats, the conclusion is stunning. In the Milky Way, there are estimated to be hundreds of billions of planets, of them billions rocky. For every flicker of the night sky, there is someone's orbit, someone's climate, perhaps someone's ocean. Eighth fact: the space around the Earth already resembles a busy highway with invisible hail. Millimeter-sized paint chips, screws, fragments of old devices, and stages fly at 10 times bullet speed.
In low orbit, opposing streams diverge at 7 to 8 kilometers per second, and a tiny speck in such an impact acts like a miniature explosive. Shuttle windows were once covered with pits from dust, and dents like from buckshot are found on satellite hulls. The bigger, the more dangerous. The collision of the decommissioned Cosmos 2251 with Iridium-33 in 2009 generated a cloud of debris, and the destruction of a weather satellite in anti-satellite weapon tests in 2007 scattered thousands of fragments for years. Tracking networks maintain a catalog of tens of thousands of objects larger than a few centimeters and predict close approaches. Stations and ships periodically maneuver, diverting orbits kilometers away. Invisible microscopic debris is protected by multi-layer Whipple shields. The first thin sheet turns the particle into a plasma cloud. The second dampens the impact. Around critical compartments, armor of honeycomb panels is installed. But the best protection is not to litter. There are recommendations to bring devices out of low orbits into a controlled descent within about 25 years. Passivation requires draining fuel and discharging batteries so that old devices do not explode on their own. For geostationary orbit, there are graveyard altitudes where defunct satellites are raised on a farewell impulse. Active cleanup is also being tried. Nets and harpoons in the Remove Debris experiment, an ion shepherd that gently pushes debris with a plasma jet, aerodynamic sails for braking in the upper atmosphere. The solar cycle raises the thermosphere. Resistance increases, debris burns faster. But communication mega-constellations add traffic and demand discipline. Orbit is a common yard. Ignoring its ecology means playing cosmic roulette with fragments that don't need aim to hit.
Ninth fact: the Sun has an invisible cocoon, the heliosphere, a bubble of rarefied solar wind plasma that rushes towards interstellar gas and gradually loses to it in terms of pressure. At its border, the heliopause, the star's influence is exhausted. Interstellar magnetic lines rearrange the pattern, particle density changes, and the flux of galactic cosmic rays becomes noticeably higher. The Voyagers reached this border, two automatic ships from 1977 which have long passed Neptune and Pluto and continue to travel like bottles with a message in the wet darkness of interstellar sea. First, they crossed the shock wave, the termination shock, where supersonic solar wind abruptly slows down. Then, one after another, they crossed the heliopause. There are no longer direct eyes to measure plasma density. But Voyager 1 hears the interstellar with its ears. The plasma antenna catches the tremor of the electron gas, oscillations that arise after powerful solar flares. And by the frequency of this flute, they calculate the density of the surrounding medium. Communication is carried out through the 70-meter parabolic antennas of the Deep Space Network. Hypersensitive receivers extract a handful of bits per second from radio noise, and the signal transit time is measured in tens of hours. This is the scale of distance. Power is supplied by plutonium thermoelectric generators. Decay heat decreases year by year, and engineers turn off instruments one by one, like lights in a departing train, to extend their lifespan. On board is the Golden Record, a copper-gold disc with greetings in dozens of languages, heartbeats, whale cries, a coordinate map of pulsars, and the diagram of a record player. The chemical relief of the cover is an instruction for those who guess to read it in a million years. The Voyagers are already beyond the Sun's house, but still very close by galactic standards. To the edges of the hypothetical Oort-Clyde, thousands and tens of thousands of astronomical units, they will take longer to reach than written history exists. And yet, these old craft have brought the cosmos closer. In 1990, one of them looked back at Earth and took a picture of the pale blue dot, a speck of dust in a sunbeam. Since then, the idea that humanity has left its whisper and business card in interstellar space has ceased to be literature. It is a dry fact of telemetry and communication logs. 10th fact: in the universe, there are ghost particles that barely register matter, but precisely because of this, they carry the most honest news from the depths, neutrinos. Every second, tens of billions of solar neutrinos per square centimeter pass through your fingernail. They are born in the thermonuclear heart of a star, penetrate the Sun and Earth with minimal interaction, and fly onward. For a long time, detectors observed fewer of them than models predicted. The solar mystery troubled physicists until vast reservoirs of pure and heavy water in Japanese mountains and Canadian mines revealed that neutrinos can change their guise en route. This involves quantum oscillations between electron, muon, and tau types. This implies neutrinos possess mass, tiny but non-zero. In 1987, several underground detectors almost simultaneously registered a couple of dozen neutrinos from a supernova in the Large Magellanic Cloud. The signal arrived hours before light because the neutrinos had escaped the collapsing core before the shockwave breached the stellar envelopes. Today, we also capture much more energetic travelers. The IceCube Observatory is buried in a cubic kilometer of Antarctic ice, where thousands of photomultipliers listen for brief blue flashes, traces of relativistic particles born when a neutrino finally collided with an ice molecule. Some of these events trace a connection to active galactic nuclei and blazars, distant engines where supermassive black holes accelerate cosmic particle jets to near light speed. Once, a high-energy neutrino and gamma-ray bursts pointed to the same aggressive source. Neutrino astronomy renders the cosmos transparent where photons are forbidden, through dust, through stellar depths, from epochs when matter is opaque to light. Coupled with gravitational waves and electromagnetic spectra, it transforms the observation of the universe into a three-dimensional investigation. Who accelerated the particle? Where did it deviate? Which core collapsed? This knowledge was born from silent flashes deep within a glacier and the quiet counting of photons in giant underground vats. And it is precisely this that connects nuclear reactions in the bowels of stars with the cold night above our heads.